In this question, we're looking at how the order of reaction is related to the graph of concentration of a reactant over time as the reaction progresses. So let's start by looking at what those graphs are going to look like for different orders of reaction. So for a 0th order reaction, in this reaction, the concentration of the reactant does not affect the rate of the reaction. So that means that my reaction rate is going to remain constant. Now, reaction rate is given by the slope of the concentration time graph. So that means my slope is going to be constant. In other words, I'm going to get a straight line graph. And since my reactant is getting used up, it's sloping downwards. So this is showing a constant reaction rate since my change in concentration over time, in other words, the slope is constant. And that's showing that even though my concentration is decreasing, my rate, in other words, my slope, is staying the same. So this is a 0th order reaction. What about for a 1st order reaction? So for a 1st order reaction, as the concentration decreases, so that thing gets used up, our rate is also going to decrease. So our slope of our concentration time graph, which tells us the rate, is going to be getting less steep as the concentration decreases. So we're going to start with a steeper graph, and then it's going to become less steep as time goes on. So that's for a 1st order graph. You can see slope starts out steep, is becoming less steep. It's that kind of quadratic shaped curve. As the slope becomes less steep, that's showing our reaction rate is decreasing, which makes sense because our concentration of that reactant is decreasing. So the reaction rate is decreasing at the same time because it's 1st order, so those are proportional to each other. Lastly, we'll look at 2nd order. So for a 2nd order reaction, it's the same as first in that as the concentration decreases, our rate is going to decrease. However, it's more dramatic because they're not directly proportional. It's proportional to the square of the concentration. So it's also going to be a curve, but it's going to be a more dramatic, steeper curve. So it's going to start out steeper and have a more dramatic change, kind of more like that cubed style curve rather than the quadratic curve we have for the 1st order. So here again, you can see my slope starts out steep, which means I have a high rate of reaction, and then it ends up very shallow, showing I have a low rate of reaction. So as my concentration decreases, my rate of reaction decreases a lot. That's because we're 2nd order. So those are the 3 types we might see. So let's have a look at this question here. Here we have a fictional scientist carrying out a fictional reaction. Here's our fictional substances, L2EA3 and R4. So we can see those in our chemical equation here. We've got 2 L2EA3 and R4. Then the scientist carries out the experiments to continuously measure how the concentration of each reactant varies over time as the reaction progresses, while the other reactant is in excess. That's important. So the other reactant, we've got so much of it that the change in the concentration of that reactant isn't going to affect the rate of our reaction. Okay, so first, what is the order of reaction with respect to the concentration of L2EA3? So here's our graph of L2EA3 over time. It's that straight line sloping downwards. So looking at our options at the bottom, that matches up with 0th order. And remember, it's a straight line because that means our concentration change over time is remaining constant. Our slope is constant, meaning our reaction rate is constant. So the fact that our concentration is decreasing isn't affecting our rate of reaction. So it's going to be 0th order for L2EA3. For R4, if we look at our graph here, we have that really steep curve that changes quite dramatically. So we start out very steep, a very high reaction rate, we end up very shallow, a very slow reaction rate. So that looks like our second order graph down here. So this is going to be a second order reaction for R4. And then our final step is just figuring out our overall order of reaction. We just know we have to add them up. So 0 plus 2, which gets us 2. So our overall order for this reaction is 2. Let's do one more of this type. So in this question, we again have a fictional scientist with a fictional reaction with substances M6E4 and R2. So we can see in our reaction, we've got M6E4 plus 7R2. We're told the scientist experimentally determines the reaction is 0th order with respect to M6E4 and first order with respect to R2. Then we're trying to decide what will the graph look like when the scientist continuously measures how the concentration varies over time as the reaction progresses. Okay, so first we're looking at M6E4. We're told this is 0th order. So looking at our options at the bottom, 0th order looks like that straight line sloping downwards. So that's going to be graph 1. And the reason why it's a straight line sloping downwards is that slope is our reaction rate. Since it's a straight line, our reaction rate is constant. That means that as our concentration is changing, it's not affecting our slope. In other words, it's not affecting our reaction rate. So that's 0th order. So the graph is going to be graph 1. For R2, we're told it's first order with respect to R2. And looking at the bottom, here's our first order reaction. It's that gentle curve. The curve shows that our slope starts steeper and ends up less steep. So our reaction rate starts high and decreases as the concentration decreases over time. So that's showing that our rate of reaction is related to the concentration, and that's first order. They're directly proportional. So for R2, it's going to be graph 2. That's the first order. So in this question, we're just matching up based on the order we have, which of these three graphs it's going to be for 0th order, first order, or second order.